Hi, everyone. My name's Sebastien, Phison CTO, and I'm here to talk to you about our AI solution and go into a little bit more detail. So before explaining, because there were a lot of questions that were asking, like, why are you doing this? So maybe I should explain why we're doing this. The way large language models work today is that if you take a model with 7 billion parameters, that's 7 gigabytes of memory, typically. It can go up or down a little bit depending on what you do, but as a baseline, 7 billion, 7 gigabytes. Consumer GPUs have between 8, 12, 14, 16, maybe max 24 gigabytes of memory. So that's pretty good for running a model. No problem. You can run 7 billion, 13 billion, anything that's under, if you have 24 gigabytes, anything that's under 24 billion will run, and that's great. But if you want to train, and I'll get to the why of it in a second, but if you want to train, you need 20 times as much memory. And sorry, when I say train, to be precise, I mean fine-tune. When you want to fine-tune, you need 20 times as much memory. So 7 billion parameter model requires 7 gigabytes to run and 140 gigabytes to train. That is well beyond what a consumer GPU has. 70 billion parameter model needs 1.4 terabytes of memory. So if you think of, like, say, for example, you had a 7 billion parameter model and a GPU with 8 gigabytes of memory, and you wanted to train that, you'd need 20 of those GPUs. Now, you're going to fit about 2 to 3 of them in a typical PC chassis. You can fit up to 8 of them in an enterprise chassis, for example. But enterprise chassis you don't have at home, and enterprise chassis, small and medium businesses, they may have them. They may be focusing on workstations. They may have 3 servers for the whole company. And so when you go to your CTO or your CFO and you're basically saying, hey, I would like to buy a bunch of extra servers to do stuff, the first question is going to be, what's the ROI? How do I know that after I've spent $50,000, $100,000, $250,000, that I'm going to have something that we can use? And the problem is that you can't even dip your toes into the water without committing to a very expensive hardware platform. And so without an alternative solution, a lot of people are just priced out of it. So a lot of the industry is focused on inference because there's no path to do fine-tune, an affordable path, I should say. There's no affordable path for these small and medium businesses to do anything with AI other than inference. And so then a solution that came about was called RAG, or RAG. And this is the idea where you can actually reference external documents, and now you can use a different kind of memory to provide a database, and the AI model can reference the database, and that's good. But it turns out you can do even better than that. And that's where fine-tune training comes in. And the idea of fine-tune training is, think of that smart person that you have in your family that just kind of has answers for everything. Or that smart person in your office has been with the company for 20 years. They know how everything works. They know where all the nitty-gritty details are, and they understand why we're doing something the way that we are when it's clearly not the most efficient way to do something. And so the whole point of doing fine-tune training is that you give it all of those Word documents, those presentations, those PDFs, and then you give it all of your customer service cases where people have called in and they say they have this problem, and instead of having to type in and figure out, well, is it this or this, and you're taking time to kind of just research your own database using the traditional keyword search, instead of doing that, if you kind of just give it this problem statement, the AI kind of works the way your brain does, and it finds correlations to things that may not be obvious, and then presents to you a better tailored set of responses. And that's what we mean by when we're saying, hey, why do giving you the competitive edge. The whole point of giving you the competitive edge is to give you access to your information in a way that it's not been available before. And so this is where our solution comes in. So previously I mentioned that the only way to do training today is to buy essentially more GPUs with more memory. Now, the thing that is not obvious until you really start digging into the problem is the memory is used to hold the model, and the compute is used to do the inference or the training, the speed, in other words. So if you need to do your training in 20 minutes, yeah, load that thing up with GPUs. But if you can wait an hour for that fine-tuned training, or maybe overnight, then you don't need that many GPUs. You could actually make do with quite a lot less compute. But right now, because compute and memory are combined together, it's the memory on the GPU card, you have no choice. Our solution decouples that, and it gives you a choice.
Sebastien, just can you go back to that, the amount of GPU memory needed for training versus inference. I thought was a really cool number, but I didn't catch it.
So it's a 20 multiplier, typically.
Oh, wow.
Multiplier by 20. And part of that is because you don't work with 8-bit parameters, you work with 16 or 32-bit parameters. And what they found is if you try to do training and your parameter size is too small, it doesn't work. The model just gets all messed up. And so you have to keep that size small. But there's also a bunch of other secondary tables that are maintained. And just things to make it work is a combination both of the parameter size, additional tables, but it's 20x.
Okay, cool.
There's another way to do that called LoRa, or low ranking adaptation, and that's about 2x, 2 to 4x, depending on how you set it up. And the thing is, it'll either, oh good, make sure I didn't click it. It'll either work or it doesn't work. That's kind of the neat thing about LoRa is, so you run it through, and if you see an improvement, it worked. And if it's not really doing anything, it doesn't work. So then the fallback is to go to full-size training.
So what did DeepSeek, was that one of the tunings they did as far as the compression?
I'm so sorry. That's not a topic that I've dove into, so I can't really talk about it authoritatively.
Okay. There's all different ways, I guess, as you're saying, to compress the size if you need to, but normally 20 to 1, and then the other one's 2 to 1 if they LoRa?
2 to 4, depending on how you set it up.
Okay.
So then are you finding that, full disclosure, I had to look up the difference between fine tuning and RAG, okay?
Mm-hmm.
The full disclosure. So are you finding, because of that, and because I do talk to a lot of people, but I don't spend all my time with the AI people, are you finding that companies or enterprises are not fine tuning because of this problem? In terms of their data pipeline and how they're doing it, how they're executing on how they're going to bring the model in.
Yeah, it's a bit speculation on my part, because it's not like people stick up their hand and say, I made this corporate decision and this is my plan because of X or Y or Z.
Yeah.
But I tend to look at it from a different perspective. It's like, what do I know? I know that fine tuning requires a boatload of memory, which greatly increases your cost. It goes from buying one workstation or one server to having to buy 8. And at the end of the day, when you're talking about putting out a $200,000 PO or a $1 million PO, then the questions are going to start, your CFO or whoever's responsible for the budget is going to start asking questions like, can you explain to me why you need this? Can you explain to me why it will work? And then you'll get grandiose statements, right? Oh, it'll help us with this, this, and this. And then they'll say, do you have any data to support that? And the answer is no. And they can't even get the data to support that, because you have, like, the ticket to enter is huge. And since you can't do like a small proof of concept without paying that price, often they just don't do it, or they look for alternatives. RAG is a good alternative because it starts to bring that domain-specific knowledge in. And I'm not saying it doesn't work, and I've got a slide that kind of shows how the quality improves as you do more specialized training. So it's not that it's zero value, it's that you can do better.
Yeah.
Okay. So, oh, sorry, go ahead.
I was going to say, yeah, Brian Martin, Signal 65. For a flash company, it looks on this slide like you've invested a tremendous amount in the software around this problem.
Yeah.
And just leveraging the fact that you also happen to be an excellent flash company. Can you talk a little bit about the investments, or will you talk a little bit about the investments you've made in the software stack around this?
Right. So let me think how to answer this. So we're starting with our SSDs. And I do have a slide that goes into a little bit more detail on the SSDs themselves, but I can just mention that we're using, if you're familiar with NAND, we're using the SSDs or the NAND in pseudo SLC mode. So we start with a TLC, a 3-bit per cell. We switch it to SLC mode. And what that does, the reason you do that is twofold. One is that it improves your read-write speed, but two, it increases your endurance, your raw endurance, by a factor of 20. So you go 3 to 1, you'd think, I get 3 times the endurance. No, you get 20 times the endurance. So it means that you essentially, as a starting point, in other words, instead of having an SSD that can support 1 drive write per day, you can support effectively 60 drive writes per day. And that's a combination of a few different things. But so that's a good starting point. We actually took it one step further, and we will support 100 drive writes per day. And we have a slide to explain why you need that. It's not that if you're working with smaller models and you're not doing that much training, you don't really need 100 drive write per day SSD. But our goal is to not create, we want the user to have a good experience, and having drives that wear out and die and you have to replace them like brake pads, it's going to be pretty irritating to most users. So we've essentially configured it so that the SSDs that you buy will last the life of the PC or the server, which is 5+ years, depending on how you use it. So that was the intention, to make sure that it doesn't create a negative user experience. Now, to answer your original question, from a software investment standpoint, I think we have 3 teams now that are working on different aspects of it. There's one team that's working on the middleware, which we call aiDAPTIV Link. There's another team that's working on the user interface that we call ProSuite. And then we have some teams developing, we don't cover that in this presentation, but we also have teams that are developing different types of agents and mini services that leverage on top of that. For example, you can connect, or we have one solution where you can basically, the premise is that you're kind of working with it like you would a junior employee or something like that, but maybe asking tasks that are kind of unrealistic. So you could take an email or a chain of email, send it to the AI agent that is connected to your Exchange server, and then ask it, hey, can you summarize this and translate it to Spanish or Russian or what have you? Or French or German. And so it will do that, and then it comes back a few minutes later with, here you go, kind of thing.
Got it. Okay. I presume these are Gen 5 PCI 4-lane.
This one's a Gen 4. Our next one will be Gen 5.
Yeah.
And when Gen 6 is commercialized, we'll have one in Gen 6 as well.
So the aiDAPTIV Link, that's something you wrote? It's not an industry standard or
correct.
Open source? Okay.
Yeah. So internally, what it's doing, so PyTorch has a whole bunch of hooks and callbacks and stuff like that. So essentially, when PyTorch hits a condition, like say, for example, out of memory, there's a callback that it calls. And so leveraging the capabilities within PyTorch, we have a bunch of callbacks and intercepts that essentially allow this or enable this to work. So I've been stuck on this slide quite a bit. I'd like to jump forward just a little bit, and I think this will start to address and provide a little bit more color to how all of this works together. So the basic idea is that the middleware is sitting in the PyTorch, it's intercepting callbacks, and it's between the GPU and the SSD layer, the hardware layer. And so when PyTorch hits a situation where normally it would throw an error, our middleware comes in and essentially provides a handler for that, and makes it so that at a high level, the PyTorch basically never runs out of memory, and it is how can I say this? PyTorch never runs out of memory, and it provides a seamless expansion to the memory pool without having to have a one-to-one correlation with GPUs. And
so, just a quick question on that. Tell me how aiDAPTIV Link or aiDAPTIV Cache is different than just a normal OS swapper.
I mean, fundamentally, it's a swap file. If you think of it, and you kind of get rid of all the fancy words, it's a swap file. So, but the thing is, the swap file is designed to run on the operating system. It's not designed to run on the GPU, and there's no integration with PyTorch. And you might think, well, why doesn't PyTorch add it? They didn't. There was a time where OSs didn't have a swap file, and eventually it was added. So, eventually will it become a core service? Possibly. It's hard to say, but currently it's not a service that's available through PyTorch.
Okay, and I mean, you use traditional swap algorithms, or do you? I mean, how do you? What type of swap algorithms do you typically use for it?
Oh, I've got a slide on that.
Okay.
So I'll get to it. And I think the picture will help. I could explain it verbally, but I think having the picture to support it will help. So if you could bear with me, I'll get to it.
Okay, yeah, it's, I've been listening, and you're talking about very interesting stuff, but I'm getting to the point of I want to hear how you do it.
Yep, totally get it. Okay. So I think it's like about 4 slides later. So this one, I'll just cover this one really quickly. This addresses the question, hey, why do you need 100 drive writes per day? Who the heck needs 100 drive writes per day? So if you're looking at 6,000 AIDA, which is about a $2,000–3,000 GPU, I believe, So if you're talking about a workstation that has 6,000 AIDAs, if you were to do training 24/7, which we know is not realistic, right? We're looking at the worst case. Can you burn this thing out? And the short answer is no. By design, we wanted to make sure that you couldn't. So if you were to do 24/7 training with four 6,000 AIDAs, you would need about 15 drive writes per day, and this is true for the W7900 Pro from AMD. And then if you look at the server configuration where you have 8 of them, it just basically doubles. And if you're looking at enterprise grade GPUs, then they're a lot faster. And so you can do about 60, you need about 60 drive writes per day to support H100s, MI300s, and Gaudi 3, for example. So the point here is to reassure everyone, hey, you're not going to put this drive and then have it die after 6 months and then have to buy another drive and another drive and another drive. This one, you buy the system, it's good for the life of the system. And then you can just focus on using the system instead of maintaining the system. Our ProSuite, and I'm about to go into the details of how it works internally, but we started off with just a command line driven thing, and the feedback that we got very quickly is, hey, for this target market, people really want something that's easy to use. They want it to be no code GUI. They want to be able to click on things and just say, you take care of all the little nitty gritty details, and then I want you to take these files, run them through the training session, and then do the fine tuning, and then generate the file and give it to me. Because ultimately, these large language model or large language models are like 8 gigabyte files or 70 gigabyte files. So the whole purpose of our GUI is to make that easy, and then coupling that with the training that we offer. The idea is that with a couple hours of training, pretty much anybody in the office can be set up to be the person who kind of takes the documents and puts them into run. And then with some of our partners, they're working on automating that solution so that when you take the files, for example, and you put them in this folder, then the whole system picks it up and does the training automatically, and nobody's involved. It just happens, and the model gets smarter over time. So this goes into the why. We did a scenario where we had a set of questions that were industry specific. I think they were related to NAND. And we asked some questions of GPT-4o, and basically the more blue and gold that you have is good. The more green and silver that you have is bad, because the 20% or less answer, 40%, 20 to 40% quality answer. And so what we see is GPT-4o, even asking questions that are quite industry specific, is not bad. If we take Llama 70B and we just do GPT-4o with RAG, it's not bad. If you take Llama 70B and you just take it off the shelf and then you connect it to your RAG infrastructure, it's also pretty good, but you do have some of those low quality answers. And what we found is if you do LoRa and fine tune, the amount of good answers increases substantially. And the thing is, when you have an answer that's like 60 or 40% correct, that's like, if you have that relative in the family that kind of understands computers but doesn't, and then they try to talk about technology and you're like, you're kind of right, but not really. You want to avoid that. You want those low quality answers to be smaller. And so the point that we're trying to make here is that you can take an off-the-shelf open source model and essentially end up with results that are better than this big giant industry, this big company with GPT-4o. And GPT-4o is great, but if you're asking it domain-specific questions, there's an advantage of having that model actually be trained on your data. And this goes into the details that I think you were asking about. So normally when you do training, and let's say you're doing Llama 70B, so that's going to need about 1.4 terabytes of memory to train. What PyTorch does is it looks at the GPUs that you have, and in this scenario we're proposing GPUs that have 48 gigabytes of memory. So they're those mid-tier pro-grade GPUs. They're a little bit bigger than what you see on the consumer side. So in this scenario, the 1.4 terabytes of memory needs about 32 GPUs to fit. So if you take 1.4 terabytes and divide it by 48, you end up with 30, 31, and then you actually need a little bit of space to put your training data into it. So you end up with about a pool of 32 GPUs. And if you're taking workstations, that's 8 workstations. And if each workstation costs $30,000, $40,000, $50,000, multiply that by 8, that's your cost to get in the door to be able to do training with these larger models. And so normally what PyTorch will do is it'll slice up your model into 32 slices and then distribute them across the GPUs. And then somebody hits the go button and then you feed in your first batch of data, it does the training, feed in your second batch of data, it does more updates and so forth until you've gotten through all of your data. What our solution does essentially is it works with the GPUs that you have. So in this configuration, we just took one node and you have 4 GPUs. Each of them have 48 gigabytes of memory. Like everything's the same. We're just using one node instead of 8. So from PyTorch perspective, it doesn't really know or care. It just responds to all of the calls that it makes to discover the capabilities of the system. It just goes, oh, okay, I'm great. I'm not going to run out of memory. And so it slices up the model and then puts the first 4 slices on the GPU, and all the slices that don't have a home will sit on the SSDs. And then as soon as one of the GPUs finishes doing that round of training, it says, hey, I'm done. Our middleware comes in, takes all the data off the GPU, puts it on the SSD, and then takes the next pending slice and puts it on the GPU.
Gathering that the big value here is cost savings, space savings. You're going to get some performance improvement by not checkpointing across a field of workstations, but you're going to take slightly longer because you're paging these things in and out. You have a trade-off slide that shows.
Yep. And I'll just sort of tell you where this is going. The trade-off is, it's kind of neat. Thankfully, it's linear. So if a job would have taken 8 GPUs, would take an hour, if you cut those GPUs in half, you have 4, it doubles the time. So if you have the amount of GPUs, you double the time.
If the GPU's flat out, if I'm not doing it for the memory, and the GPU's not flat out. You're assuming if the GPU is running at 100%, then it's linear.
Right.
I thought one of the propositions earlier was I did all this for the memory, but I can't feed the GPUs. The GPUs are running at, say, 50% because I'm really there for the memory. Or you're saying in training, they're pretty much always flat out.
Sort of. You end up being, so if you look at the capabilities of the tensor cores on NVIDIA GPUs, for example, the tensor core is what does the matrix multiplication. So the matrix multiplication, like if the data that it needs to work on was sitting in its L1 cache or directly in the registers, it's insanely fast. But the reality is that it'll do the calculation and then it waits for the next round of data to come from the memory, whether it's GDDR or VDDR, it goes by different names. Whether it's the GPU regular DRAM or a high bandwidth memory, you're talking about 100 gigabytes per second versus 800 gigabytes per second per channel. But even though those numbers are really huge, they are substantially slower than what the gate logic can do. So no matter what, the gate logic's kind of always waiting. And you can't get around that unless you could have something even faster than HMB, like 100 times faster than maybe you might be able to saturate the compute capabilities. So when they talk about LLM, all LLMs are fundamentally memory bound, which is memory is the bottleneck. You either don't have enough of it or it's not fast enough. Even when it's HMB, it's still not fast enough to saturate the compute capabilities. Okay. And so this kind of talks about the linear trade-off scenario. So in this scenario, and the system configuration is in the bottom right, but we're basically assuming a workstation with 4 GPUs, and each 4 GPU has, I think, 48 gigabytes of memory, which works out to a pool of 192 gigabytes across the 4 GPUs. So in that scenario, if you're training a 7 billion parameter model and you multiply it by 20, that's 140 gigabytes, and that fits nicely within the 192. It consumes about 68% of it. You're good to go. You can, on this configuration, you can train a 7 billion parameter model. You don't need our solution. It'll work just fine with the native solution. So the orange represents the configuration using aiDAPTIV, and the blue represents the configuration using the GPU only. And so in this case, you need four GPUs, and you have it in both situations. If you, say, wanted to train a 13 billion parameter model, without our solution, it doesn't run. You just get an out-of-memory error. You would actually need 6 GPUs for that to have enough memory to train normally. But with ours, it keeps the 4 GPUs, and what you see is it takes a little bit longer. It's a little bit harder to see on the 7 to 13, but if you look at 7 to 70, you go from 0.4 hours to 4.4 hours, and that's about a 10x multiplier. Not perfectly, but close. And so 7B and 70B, 70 billion is 10 times bigger, and the time is 10 times longer. So it's what I was referring to from a linear scaling standpoint. And just to give you an idea, just to go back to the beginning of the earliest statements I made at the front of the presentation, 7 billion needs 140 gigabytes to train, 13 billion needs 260 gigabytes to train, and 70 billion needs 1.4 terabytes. So in the 1.4 terabyte configuration, you need 32 GPUs. And this is where we're talking about the costs add up quickly. Now, the next question somebody would bring up, and you'll see this in the forum, is, hey, why don't we just all stick with 7 billion? And it kind of comes down to the nature of the questions you want to ask it. For very specific tailored tasks, often 1, 3, and 7 billion are just fine. But if you're trying to ask it more nuanced questions, give it really long prompts, you generally get substantially better results with larger models. We did the same thing in an enterprise configuration with 8 GPUs. Here we're using A6000s, but fundamentally it's the same result. The main thing that we want to emphasize here is that there's, I mean, you could kind of say like, there's no reason why you can't train a 180 billion parameter model on 4 GPUs or 8 GPUs. What you're trading off is time. So here we double the number of GPUs. So the impact is you would think if I go from 70 billion to 180 billion, which is roughly 2x, it should take 20 hours, and it would, but we double the number of GPUs in this situation, so it's 10.
Right. Do you have a chart? What I'd love to see in this chart is the cost delta, because I imagine it's a dramatic cost difference. If I had, 75 GPUs on the right, what would it take to do that training? Would it be half the time, a third of the time? Would it be the same 10 hours?
So if you had 75 GPUs, it would take you about 40 minutes.
Okay.
So, and that's the thing, right? If you need the data, if you need the training to finish in 40 minutes, buy the 75 GPU system. But it comes with a 75 GPU budget.
Right.
And if you need it, it is what it is. But a lot of organizations, because depending on who I talk to, when you talk to the people that absolutely need speed, they kind of get a little bit angry. It's like, why would I want this? This is garbage. I don't want slower. This is dumb. But when I talk to small businesses that don't have that need, they're like, wow, 4 hours? And I save how much money? That's great.
I want to see that slide.
Yeah,
I want to see the dollar slide.
I didn't make that slide, but basically if we take this one, you can assume about $40,000 per box. So in the 30 GPU configuration, it's 8 boxes, so it'd be 8 times 30, $40,000 kind of thing.
That feels compelling.
Yeah, and the servers are a little bit more expensive. They're in the $50,000 to $60,000 range, so it'd be $60,000 per server, and each server can hold about 8 boxes, so you need 10 of those. That brings you to the $500,000, $600,000 price range. Or with ours, you can get by with 1, and you don't have to put 8 GPUs in there. If you're okay for it to start Monday and be done Wednesday, because it just doesn't matter. Like, it's not like your AI is dead. Your AI on your deployment server that's doing the inference is still running. This is the update.
Right.
Maybe the update can come Tuesday. And if it can, you don't need 8 GPUs. Maybe you have 4 GPUs in that box. And each GPU is about $3,000 to $4,000 in this price range. So that saves you another $20,000.
Right. And power and cooling.
So a question here is that I think if I understand it correctly, what you're really doing is adding a SSD-backed swap cache to a pipeline that didn't include it originally.
Correct.
Okay, which makes perfect sense. As an old systems guy, I get that completely when we design, right? It's L1, L2, now you've got an SSD backed
an L3
cache, right? That's speeding up the pipeline. What is it, other than just adding that to the system, is there something special about Phison hardware, Phison technology that we're leveraging here? Or is it, that's where I'm trying to get. What's Phison's special sauce in this?
Sure. Well, the basic special sauce, I'll answer that in 2 parts. The basic special sauce is 1, we enable it. 2, we provide commercial support. Kind of like anyone can download Linux, but people pay for Red Hat Linux to get the support contract that comes with it. So we're offering that capability, which to a lot of organizations who don't have a really big IT team, that's worthwhile.
Absolutely valuable. Don't want to denigrate it in any way. I'm just trying to understand what you're bringing to the table.
Right. So we that's the part A. Right. Or sorry, our 1.0 solution was, hey, let's bring this to the market.
Gotcha.
Our 2.0 solution, because Phison, we tend to describe ourselves as a controller company, but we're not really a controller company. Yes, we make the controller, we make the firmware, we make the module, we make full, complete, SSDs and take those to the market. But that controller is all of our own IP. So within an integrated circuit, each functional block is often called intellectual property. That's what IP stands for. So all the IP that goes in it, we design in-house, which means that we can make it do anything. And so we're actually looking at, in the process of developing, adding compute capabilities to the storage controller to actually offload some of the tasks that the GPU does. Obviously not the big matrix operations. You need matrix engines for that, and we don't do that. But if you look at other steps in the training pipeline, there are things that you could actually just offload to the SSD. You can offload them to the CPU as well, but you don't have to in our situation. And so when you're looking at like a workstation that has 4 GPUs, and if you're training really large models, you might have 2, 4, 6 of these offload AI 100 SSDs, or the upcoming AI 200, I think is what the next one will be called. And so if those can also essentially act as a complement to the GPUs, you start to go beyond what other offload solutions offer, because ours comes not only with the offload capability and the commercial support, but now it also comes with each of those SSDs is doing work in the AI pipeline.
Gotcha. And there's a lot. That would be huge. There's a lot of value in that, because I could foresee you could do something like a DMA out of the SSD cache to the backing store without going through main memory or CPU.
That helps. It turns out it helps less, because we looked into it.
Right.
Of the total workload, like most of the time is spent waiting for the GPU to finish.
Right.
The transfer time is about 5%, and even if you were to make that 50% faster, it's a 2% improvement, a net 2% improvement. So it's we'll do it eventually, but it's not the top priority. There are other things that we can do that will provide even bigger improvements in performance, like adding compute capabilities to the SSD, which can add like a 30, 40% improvement.
Gotcha.
Go ahead.
So far, Jim Sprinsky, ZDC, this sounds like unicorns and magic fairy dust to me. It just seems extremely wonderful. Let's talk nitty gritty. How much more or less power and cooling does your solution bring to the table versus, like you're saying, right? Instead of buying 20 GPUs, I'll buy 4.
Yep.
So is there a compelling case from an energy consumption or lower energy consumption and power and cooling?
It depends on how you look at it. So there are 2 ways to look at it. If you look at it total power, right? If I make something take half the power, but I make it run twice as long, that's neutral. It's the same. You burn the same number of joules, the same number of watts, kind of thing.
Sure.
But if you look at it from how much power do I have to supply to the box and your whole power delivery infrastructure, an 8 GPU box starts to need like a lot of watts of power. And so often you're moving from the 120 to the 240. You've got a power delivery unit that adds a couple $1,000s to your rack, kind of thing. And plus your data center or your space, if you're a smaller company, it's that room that has the computers in it with a little bit of cooling. You have to be able to have that power. So with our solution, the advantage of having less GPUs is that you can actually, if there's a constraint for your deployment, you can tune the power consumption, the instantaneous power consumption of the box to match what your circuit can support.
Okay.
So related to that, can you tell us what your sustainability story is, what metrics you follow, what standards? Is there anything, other than the normal, we do our best?
Well, there's a yes. So one of the things that people talk about, but kind of never goes anywhere, and unfortunately, it's not going to start next week, kind of thing. But a lot of these SSDs, when the system is retired, they're not dead. They have maybe 20% wear on them. They're still 80% good. And so one of the things that we're really looking into on the consumer side for sure, but mainly on the enterprise side, but once we do one, we can do the other, is basically just getting those SSDs back, depopulating the NAND, testing it to make sure it's good, and then making a different tier of product to the point of, instead of throwing away NAND that is 80% good and shipping it off to the landfill, there are other use cases where the demands are not so high. Like obviously we wouldn't put it back into another AI SSD, which is like super write heavy and just wants the fastest performance available from the SSD. So, but there are plenty of other scenarios where maybe it's warm storage, maybe it's cold storage, where it's primarily read occasionally. That's great. You just need the capacity and not so much the highest. Because also when these SSDs are retired, they're 5-6 years old. So they're not, if we're looking at a 5-6 year old SSD, we're talking about a Gen 3. that's at best 3 gigabytes per second. And for some use cases, that's fine, but for others, it's not. So that's one of the things that we're looking into. And then, we could certainly lean into the concept that we are, and it gets a little bit fuzzy, right? But if you don't have to remodel your data center, you don't have to bring in more power, and you're not throwing away all the old stuff, that's a lot less waste that's going into the landfills or wherever it happens to go. Some cases it can be recycled. So all of that stuff is not happening because we're extending the life and the usefulness of the data center.
Thank you.
What's your research so far on products that you've made? Back to Karen's point about sustainability, is sustainability an afterthought, or is it in the forefront for your company, would you say?
It's something that we care a lot about. And in maybe about 6-7 months, there's another tier of product that we're going to start offering, which I can't talk about today. But one of the main value propositions for offering it is that we're focusing, like traditionally, there's always been this focus on TLC NAND and QLC NAND kind of thing. But a lot of like if you put 60 drives in a chassis, for example, you're going to saturate that network link with like 4 drives. So why are all of these drives Ferraris? What if they were maybe not Ferraris?
Yeah.
And then once you start realizing that in large deployment configurations, drives can have a slower, can just run slower, then you're asking yourself, do I need this class of NAND, or could I consider this other class of NAND? So that ties into the whole idea of recycling the NAND and finding other uses for it where it makes sense.
Okay, thanks.
Okay, and I'll go for a third factor in this, where product differentiator and product sustainability. Tell us some of the fun, nerdy stuff about your product that's entertaining. I mean, we're here for Tech Field Day. We want to hear how the technology works.
Right.
And I mean, you've certainly you've done a very good job of describing, what the product does, but tell us how it works.
You mean like what can you do with it once you have it?
No, the internals.
The internals, how it works.
The guts.
The guts.
Sure. I mean, it's slightly disappointing because data moves from one area to the other. That's true. And then internally, you've got these callbacks, right? But what are they? It's like PyTorch saying out of memory error, and normally you get a -1, a -1 saying error done, and it stops running. What do? We take a bunch of code, we look at the GPU pool, we figure out what's finished, we offload something. Again, it's just a basic memory move. I wish I could tell you that we're like doing these fancy backflips and stuff, but it's primarily an execution pipeline.
That's
okay.
So right now you're very early in the product family lifeline or life cycle. You're saying that now that you have this technology, you can now build stuff into the SSDs that your swap library can take advantage of.
Yes. So we're adding compute capabilities to the SSDs, but we're also at the software layer adding what we call them microservices. But you can think of them as AI agents and there are different agent flows. This is an agent flow that's designed to work with this solution, which trades off cost and performance and time.
Cool.
Okay. Did I answer your question?
Yes. No, I think the challenge here is that your technology at the moment solves is a simple yet very elegant solution to a critical problem.
Right.
Right. That is maybe targeted at the smaller, lower end side of the AI workloads.
Yeah.
We have spent the previous few days talking to people about the tip of the pyramid, and now we're down here, and the benefits are, the value prop is much more balancing price performance, not balancing prices unlimited. Performance is the only goal we care about, right? And so that's a little bit different way for us to think about it, right? And so like I said, you have it's a cache swap, right?
Yep.
And it's a very elegant solution to something that nobody thought that they would need this. Now we need this, and
Right.
you've got it, which is really cool.
What's interesting though is that this is starting to work its way up as well. So
Right.
we have conversations with the top tier people that have unlimited budgets too. They have limits. Like everyone has limits. It's just their limits are much, much higher. And one of the problems that they're running into, and this was a question that was asked earlier, is why don't you just cram more RAM on the card? It's
Right.
full. You can't. There's no more space. So the next question is, why don't you make the card bigger? Well, now you're just going to make another motherboard, but you're still going to hit the same problem, right? Even if you make the card twice as big, and you design it properly so there's no power and you have water block cooling and all that stuff, that's great. Now you've got something half the size of the motherboard sticking out at 90 degrees from the motherboard. And maybe you have 8 of those, or you go to a card system like in those telco switches where you just have these giant cards of GPUs. You still eventually run out of space to physically put more memory chips.
Well, and that's, I mean, having been here at AI Infrastructure Field Day this time and the previous time, an awful lot of the problems that people are attempting to address is how do you deliver memory to a GPU in one way or another?
Yep.
Yes.
And you're offering a very simple way to do it, going to an SSD. I mean, we hear from major networking companies, they're talking about 800 gigabit links to be able to feed memory to GPUs. And if you're using something that would be like an educational desktop machine, you're not going to have 800 gigabit networking to it.
Yeah. Well, they're even going further and they're saying, hey, what's the bandwidth on the GPU? It's 800 gigabytes, 1.4 terabytes. And then they're creating a server that has 800 gigabyte or 8 gigabit links, so 800 gigabyte per second or more per server. And so if you cram enough SSDs into a box and you give it a fast enough bandwidth to the GPU, you do get a little bit more latency, but it turns out it doesn't really matter because there is still a caching flow in the pipeline. So you can actually get to the point where you're having really big pools of SSDs connected to GPU servers with really like a lot of network links, right? The cost is astronomical. Each one of those 800 gigabit things is $20,000.
Okay, but the point I was trying to make is that it's everybody is trying to address the idea that you can't actually hold the entire working set in the GPU memory, and people are coming up with different ways of doing it.
Yep. Yes, and sorry, the thing that I was trying to get to was, I got kind of sidetracked myself. One of the things that I was trying to get to was this notion that SSDs will participate in the high end, and what they're looking for from those SSDs, I mean, you can use conventional SSDs that work on 4K I/O internally, but one of the things that people are starting to talk about is what if that I/O was smaller and closer to the size of the I/O that the GPU uses internally? And so there's a whole other branch of really high-end SSDs based on SLC with maximizing the capacity that you can put on the board of the SSD and then making sure that its number of IOPS that it can support is insane. Just 10 times higher than what the best SSD can do today kind of thing. So adding NAND to the whole memory ecosystem is happening both at the definitely at the high end. It just hasn't been productized yet, but different companies are working on it. And it's also happening at the low end through solutions like ours.
Mm-hmm.
Let's see. And then so we talked a lot about training. We actually also help with inference. So one of the problems that you have with inference is that fundamentally the thing that makes the inference like tolerable and that you're not waiting for so long for each response to come in is something called the KV cache, which actually does not mean key value in the sense of a traditional key value database. The key is a tuple with 5 entries. But nonetheless, it is a KV cache. And so the way that it works today is your KV cache is a certain size. And once it's full, there's an eviction policy. Typically, the oldest entry gets punted, but you can have any eviction policy that you want, but in many cases, it doesn't matter which eviction policy you use, so they just go with a simple one. There's no real difference if you try to intelligently pick the entry that you're not likely to use. I guess it depends if your GPU is serving 1 user versus a pool of 8 users, you might start by evicting the one that has had the least interaction, for example.
But you see, this is now you're now you start to get into the technology. Actually, the eviction policy does matter quite a bit.
LRU versus MRU has a huge difference.
And yes,
in
and
performance.
It can, but I'll explain why I'm saying that.
Okay.
Right? So
yes. And I'll tell you that I spend an awful lot of time optimizing caches.
Sure. There's a scenario where it kind of doesn't matter. So let me explain, though, because I do understand your point.
Okay.
There's a reason there's a lot of money and energy that's put into cache management or cache management policy.
Yes.
But in this particular scenario, where you essentially ask one question, then a follow-on question, and a follow-on question, and a follow-on question, right? Like you're having an interactive session with an LLM, you're essentially, you will get to a point where your session gets bigger than your KV cache, and by the time you finish processing, the second question, all of the tokens related to the first question are gone. So when you get to the third question, which is related, in this one session, you have to essentially pre-fill them, and then all of the stuff that you had from the tail end of your previous session is gone. So when you're in a situation where you essentially have 100% or more eviction rate, it doesn't matter. This is what I meant why it doesn't matter which policy you use. By the time you finish processing your question, you go to the next question, which needs all of that original data at the beginning. It's all gone. Does that make sense?
Yes, and I'll just leave it there.
Sure, I understand. I'm not trying to debate you, and I apologize for that.
Do we need a whiteboard for the two of you?
And maybe a padded room. No, but if you'll allow me, in the situation where you end up pushing everything that was in there previously, or no, actually, we'll leave that aside, right? And all that I meant to really focus on here was to say, when the new entry comes in and the cache is full, typically it's just evicted and it's gone, it's overwritten. And the way that inference works is that you essentially feed all of your queries. I'll call them words. Technically, they're tokens, and it gets all weird. But if you just think of them as words, you feed in the word of your sentence: 1 word, 2 word, 3 word, 4 word, 5 word, and then it generates the first word of the answer. And then to get the next word of the answer, you actually have to feed in words 1, 2, 3, 4, 5 of your original query, plus the first word of the answer to get the second word of the answer. Then you feed in 1, 2, 3, 4, 5, plus, A, B, the first 2 words to get word C. And then you do it again, and again, and again. And so as you're feeding in more, or as it generates new words, those new words get added to the KV cache. And once you run out, the eviction policy, they just disappear. They get evicted. And so what we did is we took the same model in both cases, but in one version we enabled aiDAPTIV, and the other one we used it in the standard configuration without aiDAPTIV. And so you ask the first question at time 0 to both of them, and they generate the same answer in the same time. And so at the 10-second timestamp, they're both finished, and they start working on the second question. Now, the problem with this particular configuration is there's not enough KV cache. So all that time that you spent doing the pre-fill, you have to do it again. So it has to do the pre-fill, and then it has to work on the tail end of the answer. And so it takes quite a bit of time, about 26 seconds to complete the second question and start the third question. Whereas on the blue side, it finishes in 20 seconds and then starts the starts the third question. So as you can see, the side on the right, even though because you would think, hey, where's it getting that stuff from? It's getting it from the SSD where the results are being cached. You would think, well, okay, the SSD is 7 gigabytes per second. That's a lot slower than 100 gigabytes per second, which is the bandwidth of the RAM on this particular card. But it turns out the compute time for doing this, it's surprisingly long. And so even though you're going over a relatively slower link, you end up with a faster real-world result. And as you keep asking questions, the SSD's got tons of space, so it just keeps accumulating more and more of the KV cache. And so we can get through all 5 of our questions, and it's done in about 58 seconds. The original one that doesn't have this KV cache offload capability, essentially at 51 seconds, it starts question 4, and then it crashes about, about 13 seconds later, it crashes, just because it just couldn't handle it. So the neat advantage is that when you're adding, you can essentially support either more users, or you can support substantially longer queries that take like large documents that are like maybe 10, 20, 30 kilobytes of words, just straight text. You can include that in your query, and it generally provides a better overall user experience that is normally only available if you have enormous servers with lots and lots of memory. And in fact, what we see is that we can, and this is a particular example using the NVIDIA Jetson, so for an industrial application kind of thing. And in this scenario, we can essentially increase the context length that it would normally be able to handle by a factor of 8x with the SSD that we paired it with. If we were to pair it with a much, much larger SSD, then the context length would be longer. And also, essentially, the time to first token recall, in other words, the time that it takes to recalculate all the missing tokens that were previously evicted, increases by, or is reduced by a factor of 14.
So have you looked at getting fancy and doing anything with predictive fill of the SSD cache in advance?
Yes. Well, that's a tricky thing, right? Because prediction is like the $10 million question. It's like, how do you know what? Like, it comes down to, will two users phrase the same question the same way?
No, much more on.
Yeah.
Even if the cache isn't being used, right? So you have the start of a conversation, right? So you can say, assume that the user is going to have a sequence of conversations. Yeah. So even though I haven't needed to use my SSD cache, let me drop tokens from main memory into the cache, pre-fill the cache, knowing that they'll eventually get evicted out of main memory into the cache, and therefore it's already there for when you next need it.
You can certainly hold on to past conversations, and you can actually create a whole indexing system where you could say, if you were talking to it, hey, remember that time we were talking about cars on Tuesday? And then would just refill everything that it had from the past conversation. You could do that. But the reason why what you're proposing is difficult is how you phrase the question and the order of words that you put in changes the order of words that are put out. And the order, like all of the sequence specifically of all the words in your questions, your answers, your follow-on questions are 100% dependent. And if you change some of them, you will get a different response.
Yeah, okay. Thanks.
But there is a lot of value in, and today we just don't do it, just start again. But imagine this, 6, 12, 18 months later, and then this whole idea of conversation recall comes in. That could lead again to a more natural experience with your LLM instead of starting from scratch or having like what some people do is they have like a text pad on the side with the query that they always ask, and then they put it in and then they continue from there. You could just say, reference my Thursday query or my standard query 3, give it a name like a file, and then go on.
Yep.
So I'm almost done. I think this is, I think I might have one more slide after this. But here, the thing that we want to sort of kind of sum up or recap the whole conversation is models are getting larger, and there are plenty of use cases where small models are fine. But when you start asking for more nuanced, more complex questions, and you're trying to get it to do more advanced correlations, generally more parameters produces better results. And we're already seeing cases where you have 605 billion parameters, 671, and 2 trillion is on the horizon. And we're seeing trends already where even at the high end, SSDs are becoming part of this flow. And so what we're doing with our solution is making sure that we can continue to provide support for these larger models. So we're actually making higher and higher density SSDs. This one right here, from a placement perspective, has room for about 8 NAND packages, which in current density is about 8 terabytes TLC or about 2 terabytes SLC mode. But this one can go up to 128 terabytes TLC and soon 256. So when you take one of these, and just to go from TLC to SLC, rough numbers, just divide it by 3, right? So if it was 300 terabytes, we could put a 100 terabyte SLC SSD, and there might be 24 of these in the server. And so we can support both high-end and low-end configurations, and then you would essentially, with these AI-100s with this SSD in the AI-100 configuration, possibly with additional accelerators within it, you then plug these in based on the size of the model that you want to work with. So most models would be fine with 1 or 2. If you wanted the really, really big models, you might be looking at 8. But the idea is that you can now tune the hardware, both from the SSD side, from the GPU side, from the CPU and the DRAM. You can tune it to match your budget and the speed that you need. If you don't need responses in 40 minutes and overnight is fine, bring that cost way down. And so our solution, it's affordable, it's private because it stays on premise, your data never leaves your control, and it ends up producing an AI agent that is more useful to your company. So that's our solution. Thank you very much.